Welcome, everybody. So it's my pleasure to introduce Sebastian Speitel from the University of Bonn. And he's going to talk about securing arithmetical determinacy. And I think without further ado, let's thanks, Sebastian, and you can start.
Brilliant. Thanks so much. Thank you all. Oh, wow. Wait until the end for that. But thanks so much for being here on a Friday night. Thanks so much for having me in Lugano. It's been fantastic so far. And yeah, the title, to summarize what I want to talk about today, I want to talk about a specific problem for a position in the philosophy of mathematics and a proposal, a philosophical justification of something formal that's been known for a while, of how it might be overcome to make the position of mathematical realism. I'll say a bit more about that in a second. Maybe a bit more feasible. And so the starting point, the type of position I want to move in the context of this talk is that of the mathematical realist. And there's, of course, a lot to be said how this kind of position should best be specified or its characteristic about it. I'll be a little bit hand-wavy here and just sort of characterize it very roughly. But the idea, or some of the core ideas, are that for the mathematical realist, mathematical statements have objective and especially determinate truth values. So all, at least all well-formed mathematical statements are either determinately true or determinately false. And they are so because of the way mathematical objects, items, entities behave. They are not so because of our cognitive architecture or our capacities for proving something or something like that. They're independent of us, whatever that exactly is taken to mean. It's even a little bit of a stronger type of mathematical realist I want to consider in this talk, namely the one who thinks that mathematical terms and theories are referentially determinate. So you might think that, okay, the only thing that's necessary is determinacy in the truth value of mathematical statements. I want to go a step further and say, no, it's really about, and I'll say something about why in a second, about mathematical terms or at least entire theories. That said, I don't, or at least essential to the mathematical realist of this talk are mathematical structures and not necessarily mathematical objects that occur in those structures. So I'm not worried about bumping into the number 17 on the streets, but I am worried about making sure that we have a way of determinately referring to the natural number structure out there. So this is sort of an informal way of saying that the type of mathematical objects considered in this talk are isomorphism classes of structures. It is the kind of starting point, so I'll just take a kind of mathematical realist position as given, but if you're not fully convinced by this position, why would you want to be a mathematical realist? There's sort of two broad lines of reasoning. The one is that it's very nice to explain why mathematics in English terms is so unreasonably effective in the natural sciences, right? Sciences seem to tell us something about how the way things are out there, and they seem to do so usually fairly accurately. What explains them being so accurate? Well, they are true. Mathematics is essential for all these sciences. So what explains why mathematics is so effective in helping these theories predict things that happen out there? Well, because the claims of mathematics are true, because they describe certain structures that are out there in some way. And the other reason is more or less methodological. Being a mathematical realist, if you already are a scientific realist, if you're not, I don't know what I can say to convince you, but if you are already a scientific realist, right, you can maintain a uniform and very attractive type of correspondence truth across all disciplines. So something that's roughly Tarskian. So statement PA is true if and only if whatever is denoted by A has the property denoted by P, and so on and so forth. And you wouldn't have to worry about mixed statements that involve mathematical and non-mathematical terms in applying different truth theories to the statements of natural science and the statement of mathematics. Now, one essential thing about the type of mathematical realist for the purposes in this talk, and I think for a feasible mathematical realist position in general, is this principle of moderation, the idea that the reference to these mathematical entities, i.e. mathematical structures, must be naturalistically acceptable. What precisely that means is, of course, a little bit vague, and there's a million ways to spell out what naturalism and naturalistically acceptable means. I don't want to spend too much time on that, but postulating a mathematical sense with which we can directly look into the universe of sets, naturalistically unacceptable, just saying that we have certain theories that describe things, and whatever these theories refer to is what these theories describe, seems naturalistically acceptable. So access to syntactic entities, theories, or equivalence classes of theories, however you want to spell that out, that seems to be perfectly within the limits of our cognitive capacities, but having this scientifically unwarranted sense that gives us direct access in some way, shape, or form seems to be rather unwarranted. So put this all in one sort of contextual claim, the position at issue in this talk is that of the moderate mathematical structural realist. That's a mouthful, and it's even only the moderate mathematical structural realist about a particular theory or structure, namely about arithmetic. So we're worrying about the natural number structure, the number line 0, 1, 2, 3, and so on, plus all the operations we can perform on it. The simplest, interesting mathematical object you might be thinking of. Why is that a position worth considering? Well, philosophically considering, well, because there is, for any type of mathematical realism, a general dilemma. Namely, if we maintain that mathematical terms, mathematical theories are referentially determinate, how can we establish this referential determinate? How can we fix the reference to the mathematical objects, entities, structures that are out there? And that problem becomes particularly acute in light of the moderation principle, right? Because whereas for physical objects that are out there, and even natural kind terms, we seem to have some more or less direct mechanisms, perception, or some sort of abstraction from the perceived things to have something where we can hang our reference on. That seems to be categorically ruled out when we're talking about mathematical structures. They're sometimes characterized as abstract, as not being inherent in the physical things, but over and above. And so we weren't permitted to postulate some sort of mathematical sense. So how is it then that our mathematical terms refer to the things they do refer to? How is it that they determinably refer? And here comes this second idea in what might be naturalistically acceptable. We just say, okay, we don't have direct or even mediated through the senses access to this mathematical things. We just say like, well, whatever our mathematical theories, our mathematical terms refer to is what makes the best functioning theories involving these terms true, right? We don't need to have access and then say, this is what it refers to. We just say it is whatever makes the best theories involving those terms true. That is what it refers to. Here's that sort of idea summarizing a quote by Boghossian. The grasp of the indefinables of geometry in this case consists precisely in the adoption of one set of truths involving them as opposed to another. How do we choose the right set of truths? Well, through the application of those theories in science. That's sort of the indispensable argument here. Would be nice if the issues were over here, but it only gets worse because especially when looking at theories of arithmetic, we know that these theories possess non-standard models. So next to the type of structure we want to pin down, the natural number structure, they possess models that look from our best theory of arithmetic, say first or Peano-Arithmetic, just as good and just as acceptable, but that are not identical with the standard structure. And the question then becomes, in light of our knowledge of the existence of these non-standard models of arithmetic, how can we maintain that successful reference to the natural number structure is possible according to this mechanism? Are you saying it is the structure which makes the best theory about the type of thing we want to describe true if there's multiple such that make these claims true and that are, from the perspective of our theory, indistinguishable? The whole thing is a particular dilemma for the mathematical realist because it seems to show that this theory is somewhat self-undermining. It's a position that says, okay, we wanna maintain that our mathematical claims determinately refer, but by the very methods we accept for theory formulation and so on and so forth, we can show that it is not the case that these things actually uniquely refer. So the whole thing seems to collapse onto itself, seems to be self-undermining, which is, of course, fatal for such a position. This kind of, and I'm happy to come back to that in the Q&A, this kind of argument is sometimes used as sort of an argument against mathematical realism in general, sort of an argument for anti-realism. I kind of don't want to see it in the context of this talk. I want to more see it as a sort of adequacy challenge for the mathematical realists themselves. It arises internal to mathematical realism. If I want to be a moderate mathematical realist about arithmetic, there's something I need to say about this internal stability. Otherwise, it seems unfair to maintain that by using the theory of first-order Peano-Arithmetic, I'm talking about the natural number structure rather than a natural number structure. And in a certain sense, there's a fairly easy way out of this dilemma, because the reason first-order Peano-Arithmetic has non-standard models is that it's a fairly weak formalism. We can't say all the things we want to say in this formalism and that we might want to say about the natural numbers. So the obvious solution is to just adopt a richer formalism in which we can say these things and hopefully show that this richer formalism is sufficient in order to pin down the or a unique natural number structure. And there's multiple ways of doing so. Which one you prefer depends on where you identify the shortcoming of first-order Peano-Arithmetic. Maybe you think, well, we know way more about subsets of natural numbers than Peano-Arithmetic allows us to say. In particular, in the deduction axiom, I want to say that it holds for all properties, not just the first-order definable ones. If you go this way, it's fairly natural to adopt a second-order formalism, which allows you to also quantify not just over natural numbers, but also sets of natural numbers, adopt second-order variables, and the second-order induction axiom. And indeed, this adoption is sufficient. Dedekind proved in 1888 that given a particular type of semantics, first-order Peano-Arithmetic plus the second-order induction axiom is indeed categorical, that is, pins down a unique natural number structure. One way to go. Another one is to say that, well, we actually know much more about the shape of an omega sequence, so the sequence 0, 1, 2, 3, and so on and so forth, than first-order Peano-Arithmetic allows us to say. In particular, we know that for every natural number, that natural number only has finitely many predecessors, right? Every natural numbers can be reached in finitely many steps. And so you might want to adopt a device that allows you to express that plane. In the context of this, this talk, I'm going to do this with a so-called generalized quantifier, symbolized by Q0 here, which stands for there are infinitely many. So the additional sentence to be adopted says, for all natural numbers x, it is not the case that there are infinitely natural numbers y such that y precedes x, i.e. every natural number has only finitely many predecessors, and then it can be shown that first-order Peano-Arithmetic plus this, notice it's still a first-order plane, in the sense that I'm still only quantifying over individual variables, is also categorical, i.e. pins down a unique model for Peano-Arithmetic plus the sentence. A third one that I want to at least mention, but then sort of neglect for the rest of the talk, because it's a little bit hard to see how infinitary inferences could be naturalistically acceptable, but a maybe not popular, but famous way of showing that we can reach some sort of determinacy is to adopt a kind of rule which allows us to infer precisely the things that was missing from our theory of arithmetic, the so-called omega rule. It's an infinitary rule in the sense that it has infinitely many premises, and it tells us that if we can establish that 0 has phi, that 1 has phi, that 2 has phi, and so on and so forth for every natural number, then we may infer that all natural numbers have phi. Adding this inference rules to first-order Peano-Arithmetic, use the theory PA omega, and that's the theory that is semantically complete. Sorry, this is just complete, not just semantically. That is, for every statement in the language of Peano-Arithmetic, either it or its negation is provable, but it doesn't yield us a categorical theory of arithmetic, so it still admits non-standard models. That is a sort of a partial solution. It yields determinacy in truth value, but it doesn't yield determinacy in reference, and so I'm going to ignore this for the rest of the talk and focus mostly about B, which is the solution I'll be arguing for, but coming back to A in concluding remarks to maybe say something about why I think this is the more promising way of going about to fix the determinacy of arithmetic. Okay, so adopting any of these solutions ultimately yields a categorical theory. Why should this be prohibited to us as moderate mathematical realists about arithmetic? And the reason is that it doesn't just feel a little bit like cheating. There's an argument that it seems going stronger formalism is doing something we shouldn't be allowed according to our position, because in using these logics that are stronger than first order logic, we're making use of resources, the determinacy of which might be just as much in need of justification as the determinate reference to the natural number structure was in the first place, right? In the second order formalism, you make use of second order quantification. That's an incredibly powerful device. How can we maintain that we have a determinate grasp of second order quantification? In the solution B, we're making use of the notion there are infinitely many. How can we claim that we have a determinate grasp of that notion? So in how far are we not sort of committing a petitio principii, presupposing what we intend to show, or presupposing something way stronger to show something way weaker? This is, of course, not a novel criticism. Here's Putnam from Models and Reality, where he says specifically about the second order solution. Some have proposed that second order formalizations are the solution, at least for mathematics. But the intended interpretation of the second order formalism is not fixed by the use of the formalism itself, and its so-called Henke models, that is, models in which the second order variables fail to range over the full power set of the universe of individuals, and it becomes necessary to attribute to the mind special powers of grasping second order notions, right? So if we look back at the theorem that established the categoricity result, we see here that PA2 is really only categorical if we assume the full semantics of the second order quantifiers. But just looking at the rules or the inferential patterns for the second order quantifiers, there's a bunch of other interpretations we could give for them. So it's by no means granted that the full semantics is the one that is automatically determined by the characterization of the second order rules. The same, of course, holds for all the other solutions. So here's Reed, saying so much in 1997, using stronger formalisms shifts the problem from the identification of postulates characterizing the natural number structure categorically, i.e. completely, into the semantics and model theory of the logic used to state the postulates, and similar statement about second order logic again from the recent Button and Walsh book. So the conclusion seems to be, okay, the move to stronger logic, it doesn't really solve the problem, it merely shifts it one level up. We're not worried about the determinacy of the natural number structure anymore, but now we're worried about the determinacy of the type of notions we use to spell out the determinacy of the natural number structure. So we pushed it one level backwards into the meta theory. We have by no means solved it. And in fact, in their 2018 book, they made this into a very general argument why the type of moderate mathematical realist I wish to defend here has no chance of solving this problem. If this were correct, this talk would be over quickly, but I hope to be able to show that there are some issues with this argument. But the argument runs as follows. The first premise is that no compact logic, that is no logic in which every inferential pattern can be reduced more or less to a finitary inferential pattern, succeeds in categorically characterizing n. That's the case because in any compact logic, you can add non-standard elements to obtain a non-standard model of arithmetic. It's a mathematical fact. And then they sort of seem to derive from that the second premise here that any logic capable of categorically characterizing the natural numbers must be articulated semantically. Why? Well, if it was articulated syntactically, non-semantically, it would have to be articulated in a compact way to account for our moderate inclinations, but we just saw that that can't suffice, so we need to articulate it semantically. But semantic articulation, premise 3, of logic stronger than first order logic requires recourse to notions determinacy of which is much more in doubt than that of n. Second order quantification, there are infinitely many. Therefore, the moderate mathematical realist is unable to resolve the issue of determinacy. And I think the mistake or the problem in this argument lies in premise 2. This assumption that, well, just because no compact logic succeeds in categorically characterizing the natural number structure, we automatically need to move to a semantic characterization. The motivation for this sort of premise is fairly natural in a lot of ways, but I think misguided. And something that underlies it seems to be the idea that the determinate reference to a particular notion, second order quantification, infinitely many, requires a complete specification of its logic. But that seems to be an additional point that is not really baked into the mathematical model realist ambition of determining the natural number structure. If it was, that would be a problem, because since it cannot be achieved in a naturalistically acceptable way, if the logic is non-compact, right, the model realist wouldn't be able to overcome this challenge. But I want to claim, and hopefully substantiate in the later parts of this talk, that a complete specification of a logic is unrelated to the referential determinacy of its notion. And that in the strongest sense, I think a complete specification of logic is neither necessary nor sufficient for referential determinacy. So we can have logics that are complete, but whose notions are not referentially determinate, and we can have logics whose notions are, well, the other way around. I forgot where I started. So neither necessary nor sufficient. I'll give some examples of how this can happen later in the third part. So with this diagnosis on the plate, let's start to defend the device needed by the modern mathematical realist to achieve referential determinacy. And based on this misgivings about the second premise, right, what is required, or what seems to be required for referential determinacy of a notion, need not be a full and complete account of the truths involving it, i.e. a semantic specification in the case of a non-compact logic. But a partial specification would be sufficient as long as this partial specification is categorical, i.e. uniquely determines the notion at hand. And at least so far, there has been no argument given why this can't be the case. Moreover, if we can give that and somehow argue that this specification is naturalistically acceptable, then the position of the modern mathematical realist about arithmetic might be salvageable. And the idea should somehow sound familiar, because it's really just what we said about what it takes for mathematical theories to be referentially determinate, transferred to the case of logical or notions in the meta theory. Namely, again, we don't have direct or perceptual indirect access to these. We again just want to say those are the notions that make a particular type of description involving these notions true. Since we're dealing with notions in the meta theory, those need not necessarily be theories, but they can also be rules or inference patterns involving these notions. Here's again Gaussian summarizing this point, that particular constant, a notion in the meta theory used to spell out the type of theory you're interested in, means that logical object, if any, which makes valid a specified set of sentences and or inferences involving it. And nowhere is an emphasis that it needs to fully formalize, to completely specify the behavior of this notion. All that is needed is that there's a unique one that satisfies the given inferential pattern. So the name of the game is whether a naturalistically acceptable, incomplete by necessity, yet categorical characterization of a notion that helps achieve arithmetical determinacy can be given. And I want to show that this can be done for the notion or for the quantifier. There are infinitely many. Once we have this, we can use the preceding argument to show that this is sufficient to get a categorical characterization of the natural number structure. And since the meta notion was naturalistically acceptably specified, so will the natural number structure have it. And to sort of get the argument going and make it a bit more formal, in order to know what type of description we can give for a notion, we should first get clear on the grammatical type of the kind of notion we're characterizing here, right? And here's sort of three statements whose surface grammar is very, very similar. There are 57 objects at phi, there are 9,123,456,000 objects at phi, or there are infinitely many objects at phi. All of them seem to have the same logical form if we just go by the surface grammar. And important to note here is that the expressions actually don't, or the numerical expressions, 57, 9 million and a bit, infinitely many, do not seem to purport to denote objects. Rather, they seem to make cardinality properties of collections of phi's, right? They say something like there are so and so many phi's, 57, infinitely many. So they are not names for objects, but they seem to be quantificational expressions, quantifiers. Now, what is a bit misleading is that, especially in the context of the theory of arithmetic, the first two claims can be expressed in a way that involves names for these objects, 57, 9 million and a bit. But of course, we can also express the same cardinality properties just by means of quantificational expressions in the standard way in which we define standard cardinalities. So the idea here is that in order to characterize the meaning of the notion infinitely many, it is actually not necessary to postulate an object infinity and then set out to describe properties of this object, like we would if we have theory of this object. Rather, it should suffice, hopefully, to specify context in which this expression bears inferential weight, informally spoken. So some ways, some inferences that we can derive on the basis of claims that are infinitely many, and context in which we may derive claims, including the expression infinitely many. Here is two such examples, hopefully fairly naturally in arithmetical context. So if we have a premise that says that there are natural numbers that phi, and a second premise that for every natural number that phi's, there's a larger one that also phi's, we should be able to conclude from this that there are infinitely many natural numbers that phi, right? So there's one, and for everyone there's one that's larger, so the chain never stops, i.e. there can't be finitely many, there should be infinitely many. That kind of looks like an introduction rule for the infinitely many quantifier. Well, it would be nice to sort of complement by an elimination type rule. That's the second one. If we know that there are infinitely many natural numbers that phi, then we should be able to conclude that there is no largest natural number that phi's, right? Because since they're arranged in a line, if there's the largest one, you can only have finitely many predecessors, i.e. will be the largest one. This is the informal idea. And the idea to sort of formally explicate it is the purpose of the next couple of slides. And to do so, we first have to talk a bit about what kind of semantic values we assign to quantifiers. And that might be a little bit more general than it's usually done in a specification of first order logic, but really the idea is precisely the same. And this idea is spelled out in the context of generalized quantifier theory, and we're here dealing exclusively with type 1 generalized quantifiers, that is, expressions that bind precisely one variable and combine with precisely one formula in order to form well-formed expressions. So the most famous ones are, of course, the universal and the existential quantifier. Formally, a generalized quantifier is a class function. It's a quantifier that takes domains and returns objects constructed from the set theoretic type hierarchy over that domain. It's easiest seen by means of examples. And we can think of these objects with Frege simply as some sort of second order property. So properties of properties. For example, the second order property corresponding to the universal quantifier is the property that is true of a set A if and only if that set is the entire domain. The second order property existence is true of a set if and only if there are some things that have the property, i.e. if that set is not empty. The second order property has at least 5 elements, is true of a set if and only if that set has, well, at least 5 members. So far, all these things are first order definable, right? It's just a slightly different way of presenting them. But of course, with this sort of mode of presentation, we can go beyond first order definable quantifier. So the quantifier, there are infinitely many, is true of a set if and only if that set contains infinitely many objects. The quantifier, there are uncountably many, is true of a set if and only if that set contains uncountably many. And in general, the quantifier, there are Aleph alpha many, is true of a set if and only if that set contains at least Aleph alpha many elements. So we immediately have class more quantifiers. But this is basically all we change, the kind of presentation of the quantifiers. And then we need to modify our usual Tarskian truth definition and the notion of logical consequence, but everything else just transfers. Here's the notational nightmare. So if we have a formula, Qx phi x, that formula is true in a standard first order models when the symbol Q is interpreted by the semantic value Q if and only if the extension of phi, i.e. all the objects that have phi in that model, are a member of the output of that quantifier over that model. And then you just define your standard Tarskian consequence relation. That was a mouthful. Let's do an example. Suppose I look at a statement for all x phi x and I interpret the universal quantifier by the universal property under point 1 here. Well, according to the satisfaction consequence condition, this is true if and only if the extension of phi in M is a member of the output of the universal quantifier over that model, i.e. is a member of the set containing the domain, if and only if the extension of phi in M is the domain, i.e. if and only if every object in M has the property described by phi. So you get your standard truth clause out, and that works very much the same for all the other things, but gives you a more or less general way to talk about quantification phenomena beyond just universal and existential quantifier in the context of first order languages. Now, the quantifier we're concerned with, the quantifier we need for arithmetical determinacy, is the quantifier there are infinitely many. That was the property that applied to a set, returns all the infinite subsets of that set. And now it is possible to show that this quantifier, this semantic value, is the unique object satisfying the following two inference patterns. So the first inference pattern tells us that from the infinite set of premise, there's at least one that has the property, there's at least two that has the property, there's at least three the properties, and so on for every n and n. We may conclude that there are infinitely many objects that have the property. The second one is kind of just the inverse. If we know that there's infinitely many objects that have phi, then there's at least one object that has phi, there are at least two objects that have phi, there are at least three objects, and so on and so forth. This is really sort of an instance of a much more general result, namely that every generalized definable class in first order logic is uniquely determinable in this way. In a different paper, we called it Carnap categoricity for a reason I hope to come back to in the concluding sections of this talk. But quickly, it's because it's based on observation that Carnap made in a 1943 book where he showed that inferential patterns usually tend to underdetermine the meaning of the usual constants. Now, this result seems to establish or establishes that these two inferential patterns uniquely determine or implicitly define, if you will, the object Q0. That is, based on these two inferential patterns, the symbol Q determinately refers to the quantifier we want to. Are we done? Not quite, because A is a non-compact inference. We have an infinite premise set, and the inference cannot be maintained when that infinite premise set is replaced by any finite premise set. So it is a non-compact inference. Non-compactness is not moderate, i.e. shouldn't be acceptable to our moderate mathematical realists. But now we got to remember, we are not, so this is a very general way of describing the inferential pattern. It only makes use of, well, schemata and logical notions. But when we're doing arithmetic, we're not stuck with pure logic. We also have arithmetical symbols, uninterpreted, but interpretable at our disposal. So if we are talking the language of arithmetic, we have available a binary relation symbol, and we can say certain things about this binary relation symbol. We can in particular say that the relation denoted by that binary relation symbol is a left minimal, i.e. has a starting point, right unbounded, continuous, linear order of the phis that are denoted in it. And if we know that we have a left minimal, right unbounded, i.e. an order that doesn't stop and doesn't circle back on itself, we know there's got to be infinitely many objects in that chain. So this is sufficient to conclude or to infer that there are infinitely many objects that are less than many. And note the statement L of phi xr is an abbreviation for a very finite first order statement. So that is in fact a compact inference. Now, of course, we're making use of arithmetical vocabulary here. That means the way we specify the notion, this notion is not logically determinate if you want. We're not just using logical vocabulary, but at least it's arithmetical determinate. That should be sufficient for the moderate mathematical realist about arithmetic, right? Because after all, we're moving in arithmetical contexts. You might think, okay, there's got to be some cheating going on here. Why am I allowed to refer to sort of a linear order and use that to specify the quantifier? Am I not simply presupposing the kind of thing I want to show in the beginning, i.e. A linear order of order omega? And this is actually not the case because we're not really saying anything about any specific linear order here. We're just saying that R is any sort of linear order. And as long as we have linear order with properties that it's left minimal and right unbounded, we have infinitely many elements. But it can be as long as it wants. It can order type omega, eta, or whatever else is out there. But it suffices to use this characterization to fix a notion of the infinite. And then we can use the notion of that infinite to fix the type of order we actually want to talk about, i.e. we can use it in this formulation of F to narrow down the consideration of linear orders to those of type omega. And the crucial idea here is that even if we have two indeterminate concepts in their interaction, they might determine each other, right? A set of concepts is introduced at the same time, and in their mutual interaction, they precisify each other. So it's not necessary to first fully precisify and specify a concept and then use it to define or specify another one. No, we can specify two concepts at the same time, even if both in isolation are not referentially determinate. That's the point Field made in a 2001 paper, where it says that we needn't first secure the determinacy of a concept before we use it in reasoning. If that were required, reasoning could never get started. We first use that very vague idea of a linear order that is left minimal, right, and bounded. We use that to specify a notion of infinitely many, and then we use the notion of infinitely many to specify a specific linear order, i.e. one of order type omega. So here's the counter-argument to Button and Walsh's argument. Premise one, the categorical characterization of N ensures determinate reference. That's something that's usually accepted in the literature, so though recently there have been some criticisms about it, particularly in Jared Warren's Chapters of Syntax, almost exactly as a premise here. A categorical theory of arithmetic can be formulated in first-order logic plus an additional type 1 quantifier symbol, as long as that quantifier symbol is interpreted as being the quantifier. There are infinitely many. That's just a mathematical fact. And then premise 3, this is what I hope the previous argument showed, that in the context of the language of arithmetic, the quantifier, there are infinitely many, can be categorically determined in a naturally acceptable manner, i.e. finitary in some sense. And from this, it follows that the moderate mathematical realist can determinately refer to, well, the notion there are infinitely many, and via this determinately to the natural number structure. You might still think, okay, somewhere there's some cheating going on, right? Somehow we need to have smuggled in some additional assumption in the background that we make use of. Somehow we seem to have presupposed what we want to show. And of course, as it stands, that question is fairly informal, fairly vague, but we can specify, right? We can ask how much more structure the language first-order logic plus the quantifier that are infinitely many actually requires than first-order. So how much extra assumptions do we put in the background for that language than we already had available in first-order logic? What are, so to say, the structural commitments of that language? And if those structural commitments are higher than those of first-order logic, then clearly we seem to have assumed something in addition to what we had assumed in first logic and must have cheated somehow. Now, the structural commitments can, on one proposal that I like very much, be measured in terms of the Löwenheim number of a logic. And roughly, the Löwenheim number of a logic measures the set theoretical commitments of a logic. It tells us how high does the set theoretic hierarchy in the background have to be, such that I have sufficiently many counterexamples to get the logic out I want to get out. So how big does the set theoretic universe have to be for my logic to work the way I want to work? More formally, the Löwenheim number of a logic is the smallest cardinality such that every claim that is refutable has a counter model of that cardinality, and vice versa. Now, by the Downward-Löwenheim-Skolem theorem of first logic, we know that the Löwenheim number of first order logic is Aleph naught, right? Every plane that has a model has a countable model. And in a paper of Bonn in 1985, we showed that the Löwenheim number of first order logic extended by any of the quantifiers Q alpha, there's at least Aleph alpha many, is identical to the cardinality Aleph alpha. So plug in Q0. So you see that the Löwenheim number of first logic is the Löwenheim number of first logic plus the quantifier. There are infinitely many. No further demands on the background structure are imposed in that logic. And in a sense, this actually isn't so surprising to think about it, because while we can't explicitly define the notion of the infinite in first order logic, it was already implicitly there, right? We could characterize it by means of an infinite set of sentences. There's at least one, there's at least two, there's at least three, and so on and so forth. Or if we have non-logical vocabulary, there's a successor function which is injective and doesn't, which is injective, or there's a linear order without endpoints or something like that. So at least from this point of view, we don't seem to be assuming more than we had in first order logic. We only seem to be making explicit things that are implicitly there, seem to reify them into a given expression, and that allows us to use that expression with that particular meaning then again in specifying the object we want to specify. How much higher are the cognitive demands? I think I'll probably have to ask a cognitive scientist to really find that out, but here's at least like sort of a very, very initial take, namely that having an understanding that there is no largest natural number is a robust enough notion to give us a notion of the infinite that suffices to categorically specify the natural number structure. And it really falls short of this like very, very extensive and robust characterization of the cardinal Aleph naught and higher in set theory. It's a very weak notion of the infinite. It's basically the notion we can go on and on and on. Okay, let me try to finish with quite a few loose ends, remarks, observations, problems about this kind of account that would have to be solved to make it fully satisfactory. And let me start by sort of contrasting it with two other approaches that have also been used to defend the position of modern mathematical realism. One is the one in a 1984 paper by Field, where he tries to argue that we have a determinate notion of finite set through applications of arithmetic and elementary set theory in scientific theory. So because the world is in such the way that it contains an omega sequence, we can use that fact to actually get a mathematically determined concept of the finite and therewith the infinite. The thing that has been criticized about the strategy is that it seems that it makes the determinacy of mathematical context dependent on contingent assumptions about the world, i.e. the correctness of certain physical theories. And it seems that this kind of gets the whole thing backwards. So Parsons says that I find it hard to see how someone could accept that assumption who does not already accept some hypothesis that rules out non-standard models as unintended on mathematical grounds. If our powers of mathematical concept formation are not sufficient to do the latter, then why should our powers of physical concept formation do any better? Right? It seems like we should first have the determinacy of mathematical concepts before we can use them in natural science reasoning, and we shouldn't rely on the contingent truth of a scientific theory in order to obtain or achieve mathematical determinacy. That seems to be a too wobbly foundation for the kind of position we want. It of course sort of leads into the question of, well, which is the right practice to seek determinacy? On Field's account, it's the practice of total science, or at least physical practice, the practice of the physicists. On the account presented here, it seems to make, in the very least, somewhat more minimal assumption, like the practice of mathematics or of arithmetic suffices. We don't need to go beyond mathematical practices. And additionally, yeah, if one uses this kind of argument, what we have is really a conditional determinacy, conditional on the truth of the type of theory that is being used in order to fix the determinacy of the mathematical. Another approach recently defended by Mursi and Topi in a 2021 paper, and similarly in the Warren book, shadows of syntax, slight modification, is the idea that, is the second order strategy, the idea that the full interpretation of the second order quantifiers, this missing piece for the second order strategy, is fully determined by the rules. And they kind of do that in two steps. They first tell us that, okay, if we really think about inference rules, they're not closed objects, but they're open-ended. That is, they stay valid under arbitrary extensions of the language. And in principle, every object is nameable in some language. And put those two together, it can't be that the interpretation of the quantifiers leaves any object out, because, well, that object is nameable in some extension of the language, and the rules that they had for the quantifier should stay valid here. I have a lot of sort of particular misgivings about this kind of argument, none of which I want to mention here, but I rather want to sort of outline some general misgivings, because I think that even if the strategy works, and I think there are some advantages to it, the solution proposed here in terms of there's infinitely many is anyway more robust and more minimal in the kind of assumptions you need to make it work. And one of the things that I'll come back one slide after this is that the failure of the categoricity of the second order formalism seems to be of a different type than the failure of the categoricity of there's infinitely many if we haven't fixed it. It runs a bit deeper, and that's sometimes swept under the carpet when we say that, oh, well, it's all sort of the same kind of indeterminacy. But the more significant objection has to do with the significant meta-theoretical entanglement of second order logic. One way, if we do accept this way of measuring structural commitments of logic, is to look at the Löwenheim numbers of that logic. And while the one of first order logic and first logic plus the quantifiers, there's infinitely many, was relatively moderate, the one of second order logic is incredibly high. If it exists beyond the first measurable cardinal, first compact cardinal, and so on and so forth. So it's very high up in the hierarchy. We're making very significant set theoretical assumption to make this kind of thing work. And moreover, central notions of the second order formalism are actually not structurally robust. So they depend very much on the actual extent of the set theoretic universe and can change their extension depending on how that universe is expanded or contracted, i.e., more formally, central notions of the semantic apparatus of second order logic are non-absolute, in particular the power set operation that is used to spell out what a full interpretation is. So either way, it seems we need to have much more significant set theoretic assumptions in place to make this kind of strategy work. And so in the very least, the solution proposed here seems to be a bit more minimal in the type of assumptions that need to be made. Of course, you might say, and I think that would be a fair objection, like, what do we actually gain with this entire exercise? After all, at most, what we have achieved at this point is a sort of relative determinacy, i.e. determinacy relative to a model that provides the semantic values for the formalism that we use to provide a characterization of the theory of arithmetic, right? If the kind of set theory in the background that assigns the value there's infinitely many to the expression there, Q0, has a non-standard model, then of course the indeterminacy that is inherited through that non-standard model obviously also transfers downward. And I don't think I have much more to say than say, like, I feel this is a general dilemma of a realist position. The explanations just will stop somewhere. I feel this is a good point, right? Access to the world on a realist account, on a moderate realist account, is always somehow mediated through theories. There's really no hope to ever find a standpoint outside all of our theorizing and, like, say, compare these theories and the kind of things that you know with each other. So the most we can hope for on the kind of realist account, this is why I said at the beginning that I would like to take this as an internal challenge to the realist, not necessarily an anti-realist counter-argument, is inter-theoretic stability. And that's something we can actually measure in some sort of way or argue for, because we might say that, okay, maybe we can't have an absolute security that there are no non-standard models of the background theory. Quite the opposite. If it's a first order theory, there will be non-standard models, but we can hope that the types of notions we spell out have a high degree of stability, i.e. are invariant through a variety of models of the type of background theory. The higher the invariance, the more stable those notions, the more independent they are of what the model for our semantic values actually looks like. And on this account, while not perfect, the notion of finitely or infinitely many actually has a much higher invariance, a much higher set theoretical robustness than second order notions, because the notion of finite is absolute among transitive models of ZFC. So as long as we assume that our background theory is ZFC and that we're dealing with a transitive model, however big, however rich, our characterization of the infinite will not wobble, whereas our characterization of second order quantification will. So it seems to be a bit, I know it's a partial and somewhat unsatisfying answer, but just reiterating the point before, at the very least, it seems to be more minimal, sort of get us more effects for the assumption. Let me finish this sort of comparison between the second order solution strategy and the strategy defended in this paper with the sort of comparison. I said before that it seems that the non-categoricity or the failure of categoricity of the second order formalism runs somehow deeper than the non-categoricity of first logic plus the notion there's infinitely many. Here's a way to sort of try to make this precise. Let us call a theory zero categorical if it determines up to isomorphism a single model against a fixed interpretation of the background theory, that is an assumed model, and we here assume ZFC as our background theory, and fixed interpretations of the logical expressions of that theory. So we assume, for example, that second order quantification has the full interpretation in the standard model of ZFC, and then we want to see, well, does that for our theory of arithmetic determine a unique model? We call a theory one categorical if we stretch the second condition. So if it determines up to isomorphism a single model against a fixed interpretation of the background theory, but we leave the ways the constant or logical vocabulary may be interpreted open. And we call a theory two categorical if it determines up to isomorphism a single model, no assumptions made. Of course, of all the formalisms we have looked at, none of the theories is two categorical. We need at least an assumption on the background theory. But notice that the logic with the omega rule is not categorical in any of these ways. Second order logic is zero categorical, but not one categorical, because even if we fix the standard model for the background theory, the formalism still doesn't tell us whether the right interpretation of second order quantification is full or Henkin. That's something we need to additionally determine. That's something Mursi and Topi try to do with their argument. Whereas the first logic plus the quantified Q0 is both zero categorical and one categorical. That means as soon as we fix a model for the background theory, the interpretation of the crucial notion used is automatically fixed. So in this sense, I would want to say that the indeterminacy of second order logic cuts deeper than the indeterminacy of the notion of there are infinitely many. Do I still have like 5 minutes? Okay, cool, thank you. Let me say some more about this notion of unique determinability or finite categoricity. It's a notion that Denis Bonnet, co-author, and I proposed as a way of spelling out what it means for a notion to be logical. Here I didn't want to make that point, I just want to use it to show arithmetical determinacy. But the original idea was that it sort of gives us a way of determining a very stable core of logical theory. That is a set of values that is highly robust and that can be, with our moderate means, determinately accessed. So just talking about quantifiers, let's assume we have a quantifier symbol Q, a type appropriate interpretation for Q, and we consider a first order model and some consequence relation, however it's given for this quantifier. That is some characterization of its inferential behavior. And then we said that this quantifier is kind of categorical with respect to this consequence relation if it respects the inferences, that is, if it renders truth preserving all the inferences the consequence relation tells us hold for this notion, i.e. if it's sound. We said that it must be invariant, right? That is sort of the semantic robustness. It is untouched by properties of objects other than their identity and distinctness. And here's the crucial condition for this talk, it must be determinate, right? It should be the unique interpretation of the symbol that is both invariant and satisfies consistency. And we call the quantifier Filkan categorical simplicator if and only if there is some consequence relation with respect to, in the appropriate language, with respect to which it is finite categorical. again, the notion Carnap categoricity comes from an observation of Carnap's in a 1943 book, where he pointed out that except for the rules for conjunction, none of the other rules actually uniquely determine standard values. Even the natural single conclusion, natural deduction rules for deduction, disjunction, negation, implication, and so thoroughly underdetermine the standard values of the constant. And so more needs to be given to make sure that our logical notions determinately reaffirm. Given that, we can now see what sort of notions are uniquely determinable. You start with a potential notion, you generate the maximal consequence relation that you deem appropriate, i.e. you pick a language with a symbol for that notion, and you generate a la Tarski the model theoretic consequence relation. You totally forget how you got that consequence relation, just look at this relation with sets of sentences and sentences, and look what sort of values are consistent, what sort of values respect this consequence relation. You collect them together in a set, then you impose an invariant for it. And if what is left after all this is what you started with, that is a uniquely determinable Carnap categorical notion. If there's more in there, then it's not uniquely determinable. If there's less in there, well, it wasn't invariant or consistent with the consequence relation. Why do that? Why is it useful? Here's sort of a partial account of type 1 quantifiers and those that are uniquely determinable. And what is interesting about this is something I mentioned in the very beginning, that completeness is neither necessary nor sufficient for referential determinacy. So look for a second at this pair of quantifiers. Here we have adding those quantifiers to first order logic makes them uniquely determinable, but yields incomplete logics. However, there are also quantifiers, for example, there are uncountably many whose logics are axiomatizable, right? Completely axiomatizable, yet they are not uniquely determinable. So completeness and categoricity for these notions seem to be completely independent. Completeness is neither necessary nor sufficient for unique determinability. And beyond this thought, this is actually something that undermines the claim that one sometimes hear made by inferentialistically inclined philosophers. And I should say, David Ripley doesn't mean it in that way, and this is totally taken out of context, but he knows that I'm doing it, and it really summarizes the sentiment very well. Namely that often one hears it say that from an inferentialist perspective, soundness and completeness serve to legitimate talk of reference, denotation, semantic value, and the like. These model theoretic terms derive their sense from the connection between models and valid inference. And if what we showed above at this table is true, this is not the case. Completeness does not at all give any guarantee that reference is achieved. Those are two separate issues. And work on Carnap categoricity is currently work in progress with Denis Bonheim and Doug Westerstelle. Okay, last slide. We talked solely about arithmetical determinacy, determinate reference to the natural numbers, but of course there was in a way an arbitrary restriction, and it seems natural to try to extend the type of approach pursued here to other mathematical structures in the hopes of showing that we also do have naturalistically acceptable determinate reference to these type of structures. There's multiple ways one could be doing that. One could simply repeat aspects of the approach yielding the determinacy of the natural numbers pursued in this talk. So for example, one could replicate the process above, and that's a fairly direct result for the determinacy of the ordering on the integers, right? If I add to my favorite characterization of the ordering of the integers, the sentence that for any two integers, there's only finitely many numbers in between them, one would categorically characterize that structure. One can go further. One can use notions whose determinacy we have shown here as bootstrapping devices for other notions. So we can use first order logic plus the quantifier, there's infinitely many, to try to define other generalized quantifier who are then derivatively determinate. Here's two more or less simple examples of that. Or one can do what I tried to sort of hint at with that field code. One can just throw a bunch of generalized quantifiers into a logic at the same time. And even though every single quantifier in isolation is not determined, in their interaction, they will ultimately just narrow down their intended models. And then we have a language that as a whole is determinate and which we can use to characterize, hopefully, a host of interesting and important mathematical structures. That's it. Thank you so much. I look forward to the second.